In this short lecture, we'll talk about the qualifier volatile. A compiler can translate a C program into a binary executable. During the translation, the compiler can make aggressive performance optimization. For example, compiler can cache a variable in a register to reduce the number of memory accesses. Compiler can also reorder computations or eliminate useless and redundant computations. However, sometimes things don't go as planned. Optimization can break a program that was working well. Let me show you a short demo. In this C program, the cystic interrupt handler only performs two simple tasks. First, set the variable flag to 1, and then turns on the green LED. The main function first initializes GPIO and cystic interrupt, then waits until the flag is set, and finally turns on the red LED. Let's first use the default compiler setting, which applies the minimum amount of optimization. Compile and build the program. Download the program. Click the Reset button to run it. As we can see, both the red and green LEDs light up. The program works exactly as we expected. However, let's see what happens if we let the compiler perform some optimization. There are three levels of optimization. Level 1, restricted optimization. Level 2, high optimization. Level 3, maximum optimization. Let's choose level 3. Compile the program, download it, and click Reset and run. Surprisingly, only the green LED lights up. The program has failed to turn on the red LED. Let's find out what was going on. Here is the source code. The variable flag is defined as global and is initialized to 0. The cystic interrupt handler sets the flag to 1 and turns on the green LED. After GPIO and cystic initialization, the main function waits until the flag is set and then turns on the red LED. Under the default compiler setting, the program works exactly as we expected. Here's one example translation of this while loop. The assembly code repeatedly reads the value of the variable flag from the memory and exits the while loop if the flag is not 0 anymore. However, if we increase the level of compiler optimization, the program will be broken and fail to turn on the red LED. Here is an example assembly translation with compiler optimization. The compiler assumes that the flag value does not change because the C program doesn't seem to have changed it. Pay attention, the compiler has no knowledge that the cystic interrupt handler will be executed. The compiler treats interrupt handlers as normal functions that are never called. Therefore, the assembly code assumes that the flag value does not change. It only reads the flag value once from the memory and stores it in the register R1, and then repeatedly uses the value of register R1 without reading the memory again. The flag variable was initialized to 0, that the load instruction loads 0 into register R1. Accordingly, the BEQ branch instruction is repeatedly taken, and it essentially becomes a dead loop. Although the interrupt handler has successfully updated the flag value in the memory and turned on the green LED, the main function is blocked by the dead loop. As a result, the red LED remains off. How to prevent the compiler from making such mistakes? The solution is very simple. Declare the flag variable as volatile. When a variable or memory location is marked as volatile, the C compiler ensures that the compiled program will always read or write to the memory location every time it's referenced in the C code. As shown in the assembly program, the flag variable is always read from the memory in the loop. Let me give you another example. Suppose the variable x is declared as volatile. In this C statement, we add x 4 times. The volatile qualifier tells the compiler that the value of x may change at any time. Accordingly, the compiler should not apply any optimization to remove reads or writes to the variable x. Therefore, the compiler should not optimize the original C statement as y equals to 4 times x. In embedded systems, a memory value may be changed anytime by hardware, such as the input data register, as well as the status register of various peripherals. A memory value may also be changed anytime by software, such as interrupt handlers, or another thread if the processor runs with operating system or real-time operating system (RTOS). The qualifier volatile is designed for rows variables that may be changed anytime by hardware or software that runs concurrently. In embedded systems, there are 3 common usages of volatile. First, we should use volatile on accessing memory-mapped I/O registers. For example, we should declare the input data register of GPIO as a volatile unsigned integer, as external digital input signal may change at any time. The volatile qualifier ensures that software always reads the latest value of the input data register, IDR, whenever IDR is referenced in the source code. When an interrupt handler or a thread reads or writes to a global variable, this global variable should be declared as volatile. For example, the SysTick interrupt handler modifies the global variable counter. As a result, the counter should be declared as volatile. In summary, volatile forces the compiler to generate binary executable that performs actual memory read and writes instead of caching values in registers. Thank you for watching this lecture. Please visit the book website for more examples. See you next time.